Hi everyone. Today we will examine the problem of the model structure determination and the validation of the model once it's identified. This issue is really important because we up to now we have assumed that the model structure, and in particular let's say the family or the model within a specific family assumed in, for example, of specific structure of, for example, an ARX, Armax, box Jenkins, on down or an output error was almost fixed, and after the structure, also the order was almost assumed. So it means that the number of regressors was already defined, but really this point is still open because you need to verify the order that you assumed for explaining or determining your model. And then once you have defined and estimated your model, you need to validate it in order to understand if it fits the data that you have used. In fact, there is the title, after the title in this lecture, that says that a model is of no use if its validity is not verified, and this is a really important matter. So let's see the main points of these themes. So, as I already said, the type of model is set. So it means that normally, to now, we use the linear descriptions, and so nonlinear models will be used in the second part of this course. And then we assume that we have the so-called black box models, because normally the parameters and the structure is not known, in opposite to the white box model. The white box means that everything is known, is available. So in our case, when we are considering linear black box model, we are assuming a structure, in particular ARX, Armax, output error, or box and Jenkins. So the second point is the size, so it means the order. And as is written here, the orders of the polynomials, and in particular A, B, C, depending on the assumed structure. Of course, the true order is not present, is not available in the reality. And well, another point is that the model parameterization. So in particular, you know that you may need to transform the data, and also to perform a choice of the operators. For example, U and delta in the case you are using discrete type models. So the objective, the final objective, as we will see in the application part after these lectures, we need to introduce a measure of the quality of the model. So the quality of the model should indicate a scalar, it should use a scalar measure in order to describe its goodness. So in the sense, normally is described in the sense of mean square error, described as with this acronym MSE. So normally this index consists of a bias contribution and a variance contribution, as we will see later. So in order to reduce the bias, it means that we obtain a more flexible model structure, And in order to decrease, but this increases the variance. In order to decrease, on the other hand, in order to decrease the variance, you need to decrease the number of the estimated parameters. So in principle, I will try to sketch this function here, MSE. We will see later this specific different kind of this cost function, and of course in the independent variable represents the number of parameters. So this index increases when the number of parameters is reduced, because it means that the model is not suitable to describe our process. And on the other hand, you have a second contribution to this function, because when you increase the number of the parameters, you have an increasing of the variance. So in one side, you reduce the parameters and you have an increase of the bias here. Let's say bias. When you increase the number of parameters, you increase the variance. So in theory, there should be a trade-off, as here, indicated here. We can indicate as P star. So P star means that we have an optimal, let's say an optimal number of parameters. So it means that it represents a compromise, a trade-off between a model that is not too complex and it's enough flexible. Of course, when we also speak about, we say something about the price. Well, the price of the model in our let's say price, it means that in one case it leads to consider the algorithm complexity. So when the algorithm that it used to obtain this model can be complex, and so the price is high. On the other hand, the complexity, of course, increases also the computational time and the power. Of course, the price depends also, especially on the intended use of the model. So it means that you really need a very good model. It means that maybe you can wait for, or you are available to pay more for this model. So this is some general consideration. So let's see the model validation. So the model validation is the reason is behind these principles that is important to validate a model. Because as we saw in the previous, just I sketched this as a picture. So an underparameterized model, so it means when the model doesn't have a sufficient number of parameters, so is not flexible enough or is inaccurate. When we are using a huge number of parameters, so we say an overparameterized model, is not parsimonious, and it leads to unnecessary complicated computation, because normally the estimation of a greater number of parameters leads to may mean to use a more complicated algorithm. And let's see which kind of approaches can be used to understand or to validate the model, to validate our model. So normally you make a comparison of the outputs It depends, of course, on the purpose of your model, and there are also some statistical tests that can be used for your aim. So basic plots. What are the basic plots? Normally, you make a simulation, what we call simulation. So it means that you have the deterministic part of your model you have estimated is associated, is fed by the input, the measurement input, and you obtain the output, the simulated output. So the difference between the real or the measured output and the simulated output is represented the modeling error and the disturbances. So normally you plot the difference of these two quantities. Another interesting comparison is consists of you considering the step response with respect to the non-parametric step response. So you can understand if the dynamics are correctly described. You can go to in the frequency domain and then to compare the estimated transfer function with the transfer function of the model to compare the frequency response. As in this case, you can see here that you have the comparison between the system output and the model output, that you can see here that the maximum and the minimum of the output is in between, let's say, 3 and -2. And the error, you can see here that the order of magnitude of your error is about 1, so it's not very, let's say, the prediction, and so the error says that the model is not so good. And in fact, if you compare the frequency response, you can see here that they are quite different. So as far as I could conclude from these plots, is that the model is not so good, let's say. Another comparison that you can consider is of course the simplest one, or the most direct, is the k-step ahead predictions. So it means that you are using the data up to the instant, to the time t, you are performing k-step ahead. So you are moving k-step ahead. And this is quite important, because if the model is good, you can go, for example, ahead, I don't know, some steps. And a common choice is considered here. Is that the common choice is to have the one step ahead prediction, and then you compare the minimum square error, and you consider the one step ahead prediction obtained as we saw in the previous lecture. So using the data up to the instant t minus 1, you perform the estimation of your output at the instant t, and this is described by the optimal predictor, if you remember. Another, as we said before, another output that you can compare is called the simulation. Simulation means that you are considering the deterministic part of the model. So you have the simulated that we saw before, using only the deterministic part of your system. So this is another option of a number of indices that you can consider. And in order to compare different models, if once you have obtained different solutions, you can consider to compare this cost function, which represent in fact the mean square error, normalized of course with respect to the number of data. Another modification to these cost functions is that you may consider to normalize it with respect to the output, so you have something that is normalized. So this can be interesting. Oh, sorry, CS is okay. So it is interesting because this function is normalized with respect to the value of your output. So it's something that as a normalization is quite important. Or another comparison zone you can consider is that you make a comparison of your prediction with respect to the previous value of the measured output. This is an important test because normally when your model is unable to describe your data, it provides the output at the previous time instant because it's the best option that the model can do. So provide the previous value of your output, and you can see that in this case the residual is white, so it should be it leads to an optimal prediction, even if it's not, the model is not very useful. So there are some questions to answer. And in particular, if the model is flexible enough, and at the same time is flexible, but the model structure is large enough to cover all the possible working conditions of your system, or on the other hand, is the model too complex? When we have, for example, 2 or more candidates, which model structure should be used? So there are several different answers to these questions, and no solution is perfect. It depends on your, let's say, experience is very important. So let's see these issues. For example, is the model flexible enough? So normally the model should be able to describe all the data. And the part that is not properly reproduced or described is described or is defined as leftover. So it means that the part of the data that the model is not able to reproduce, which are the residuals. So normally the residuals are defined, as we already seen, is the difference between the real output and the predicted output. Of course, they are evaluated on the estimation of your parameters. So when the we saw in the previous lecture that when the estimated vector is equal to at least should be equal to the real vector or parameter, the real parameter vector, then it can be shown that eta is y, epsilon is white. This is define the optimality of your model. So how we can define if the residual is white? So we need to consider this. We need to compute this equation, this expression, or this variable So you can see here that is like an autocorrelation of the residual with respect to different values of the instant tau. And it represents this when tau is not small, epsilon contains the part of the data that cannot be predicted. And if this happens, it means that y could have been better predicted. There is also this is the autocovariance, a covariance or cross covariance between the residual and the past inputs. This should be small if the model, because normally in the residual there shouldn't be any correlation with the input. So this value, let's say this variable should be small, because the model should have been able to extract all the interesting part of your dynamics on the output, assuming, of course, the open loop operation. So this also indicates that the residual test is invariant to the various inputs. That is a very important result. So we need to test the whiteness of your residual. Then if the model, you can say that if the model is accurately describing the observed data, then the residual should be white. A way to validate the model is just to test this whiteness, to perform a whiteness hypothesis. So we say that we have that with H0, epsilon is a white sequence. With the hypothesis H1, epsilon is not a white sequence. And this can be done in several ways. The first one, as we saw in the previous case, we can perform the autocorrelation test. So you estimate the autocovariance of the residuals, and in the case of whiteness of the residuals, so it means that if H0 holds, then the square variance estimates is asymptotically chi-square distributed. So if you evaluate this parameter with respect to this function, so the number of data divided by the, let's say, the value of the autocovariance at tau equal to 0, summed with the square of these values for a number of degree, let's say degree of freedom m. Normally m should be several, let's say, depends on some tables, but normally 7, 8 terms. So this it can be shown that this variable tends to the chi-square distribution for the same number of degrees of freedom m. Furthermore, the normalized autocovariance obtained by the estimates as a Gaussian asymptotical, so when n tends to infinity, as a Gaussian distribution. So it means that their normalized autocovariance function multiplied by the square of the number of data tends to a normal distribution. So a typical way of using these, let's say, the first test statistics for the validation can be conducted as follows. So if x denote a random variable which is chi-square distributed with a number of m degree of freedoms, we can define the chi-square distribution for a number of degrees of freedom m and a level alpha. So the level alpha or the value alpha is the probability that x is greater to the chi-square distribution for a number of values of alpha. Normally, alpha is 0.01 or 0.1. Then, if the value of the variable is greater than the value of the chi-square distribution, normally this value can be found on tables and as a value of about 21 for a number of M8 and alpha 0.01. So it means that the residuals are not white, so we, we can reject the hypothesis of the residual whiteness. On the other hand, when this variable is lower than this chi-square variable, so we can accept our hypothesis testing. So you have in this case that the autocorrelation test, when is inside, this is the results of the Gaussian distribution, when in the axis you have the degrees of freedom, and if you see that the values, a part of tau from tau equal to 0, when is inside this 0, for example, 0.1 value, so it means that the whiteness is verified. On the other hand, the residual are correlated, so the whiteness hypothesis is violated. Another way for testing, for understanding if your residual is white, you can perform a zero crossing testing, because normally when you have a white sequence, you can, as it should be the residual, you can expect that the residual should change sign on the average every second, so for a number of times that is equal for going to the negative and to the positive value. So if we introduce the variable x hat n as the number of times that the residual changes up the time t, n, so it can be shown that this variable tend to a Gaussian distributed function for a mean value of m and p, where m is about the half of the number of data and p is 1/4 of the number of data. Moreover, so they normalize, so if you remove the mean value and you divide by the standard deviation, this variable, to this normalized variable, tends to the normal function. A cross-correlation test is another test that you may need to perform. So it means that the model provides an accurate description of the system, then the input and the residual should be correlated. So we don't have any unmodeled dynamics. It means that this autocorrelation, which in principle is computed as the expected value of the process epsilon multiplied by EU for a variable number of tau, for of course tau different from 0, should be 0. There is an important result that can be demonstrated, that this autocorrelation, cross-correlation test is violated, so this cross-correlation is not 0 for a tau, for a negative value of tau, so it means there is a feedback. A feedback is present, so you are not working with an open loop. Another indication is that if this value is different from 0, it indicates that you selected a wrong time delay in the model. So if a time delay of 2, for example, sample has been assumed in the model, but the true delay is 1, then a clear correlation between U, so the delayed input, and the correlation and the epsilon at the time t will be highlighted. And in order to visualize the correlation, you can build a model of your error. So you have that the input is U is the input of your model error, and it generates the epsilon. So the following results can be used to design an hypothesis test whatever in order to understand if the inputs and the residuals are correlated. So the normalized test quantity is x of t, which is a normalization of your cross correlation divided by the values of the autocorrelation of epsilon and u for tau equal to 0. And of course, small r epsilon u of tau is the estimated cross covariance for a number you can see here, for a number of delays, and which is provided by this expression. Then if you introduce this matrix capital R estimated of u, so 1 divided by n, and the summation of these vectors, and the small r as vector contains the value of the cross correlation for tau, for a value of tau bar tau plus 1, tau plus m, and tau is bar is some given integer. Then this quantity n multiplied by this vector and the inverse of this matrix multiplied by the vector r, so you have a scalar value, tends again to a chi-square distribution for a number of degrees of freedom n. And it can be used for the hypothesis testing. How we can, on the other hand, how we can understand if the model is too complex? So it means that we used a number of parameters that is too big, and it should be understood if the model is unnecessarily complicated, because another problem is that the model is very complex. It means that it can be sensitive to the parameter variations, and so a way is to use to study the zero-pore plot of the transfer function. So you consider the transfer function of your model, and you can put on a graphic the zero and the poles. If there is indications of a zero-pole cancellation, so it means that the model order is too high, and it is suggested to reduce the order that you have assumed, as it is shown, for example, in this graph. So you can see here that, for example, you are considering, for example, a model of order 3 here. When you are considering, so you are increasing your order of 5, you can see here that there are some cancellations, in particular these two poles. So the increased 2 poles are cancelled by other 2 zeros. So the model is suggesting that you are including too many parameters in this case. So after the cross-validation, we can check the criterion, so the cost function V1 for, or the cost function for a number of k step-ahead predictions. And because it's a problem is that if a model structure that is too complicated can include also a model of the disturbances that are present on the data. So this is called overfitting. We will find this problem also with neural networks. So we use this term cross-validation because in order to understand if your model is really describing the data outside the set of the data that you have already used for the validation, for your estimation, so using a fresh data set that is not included in the identification experiments is called cross-validation. So you are using a different set of data. And the cross-validation is a nice and simple way to compare the models and to detect the overfitted models. Of course, the model cross-validation requires a large amount of data. And of course, the validation data cannot be used in the identification because they are they have already used. And we have another principle, let's say the parsimony principle. So the parsimony principle states that one should not use extra parameters to model a system if they are not necessary. So it means that you are considering this cost function W is called Wn, depending of course on the number of data and on the parameters, which is the expected value of your estimation or prediction error. If the estimate is correct, so the prediction should be right, and it can be shown that the estimated value of this process is tends to the variance of the noise affecting the data. Of course, normally the estimation of your parameters can be different. Normally is different from theta 0. So it can be shown that this cost function, the expected value of this cost function, because it's something that should be predicted, can be explained as two contributions. One contribution depends on the mean square error. This function, mean square error. So it's something that if I'm plotting this function, is something that normally if you, again, as independent variable, you have the number of parameters, and this is let's say, the estimated value of this cost function, Wn. So you have that V1 normally tends asymptotically to 0. And this function is linearly dependent on the number of parameters. And it can be shown that this cost function asymptotically tends to this quantity. So again, the noise affecting the data and linearly dependent on number of parameters P divided the number of data N. And again, according to this function, you should find an optimal value of the parameter P, which is represented by the intersection of these two cost functions. So it can be shown that the expected value of Wn represents the average as the average as the estimated models are evaluated on the validation data. This function V1 will decrease with increasing number of parameters, as is shown here. However, each parameter carries the variance penalty that will contribute with this with 2 multiplied by the noise, the variance of the noise divided by the number of parameters. So it's increasing. Comparison of model structure. We use the prediction error method loss function V1 as a measure of the model quality. For models of increasing order, the value of the cost function, as we show in the previous slide, will decrease monotonically. And the problem is to find the lowest model order that gives a significant decrease of the loss function. Let's assume that we have 2 values of the cost function, and as the 2 values of the minimum of the cost function for 2 models orders. So for the order P1, we have V1 with the subscript V1, and for the order P2, we have the cost function V2. Then if we compute the difference between these 2 cost functions multiplied by the number of data and divided by V1, this function is as a chi-squared distribution again for a number of degrees of freedom P2 minus P1, of course, when P2 is bigger than P1, of course, because in this case V1 is bigger than V2. And then we choose the model order P1 at the level alpha if the value of this variable is lower than the chi-squared distribution for the level alpha and the number of degrees of freedom P2 minus P1. Otherwise, P2 is selected. So this is another way for selecting the right model structure. Another approach, as we saw in the previous slides, to formulate a criterion which is again a function of the loss function V1, but also penalizes the model order. So we have a cost function W1, which is a function of the loss function. So again, we have this case. So there is a contribution for according to which this cost function is decreasing when the number of parameters is increasing. So this is V1. And then we have a cost function beta. Normally beta increases with the number of parameters. And beta is a function which can be a linear function that increases with the model order P, so to penalize 2 complex model structure, but decreases to 0, so it's 0 when the number of data tends to infinity. So depending on the cost function beta and the choice of the cost function, we have, for example, different examples of penalty function. For example, what we call a Kaike information criterion, and is described with the acronym AIC. So you can see here that the IC is, for example, the variable beta is 2p, so it's penalizing twice the time the number of the parameters divided by the number of data. There is another criterion which is a final prediction error, final prediction error criterion. It's called defined with the acronym FPE, and is again the loss function multiplied by this bilinear function, where you have 1 plus p number of parameters divided by n, and the denominator 1 minus p, the number of data. There is another criterion which is called the minimum description length, where the number of parameters you can see here, instead of simply be divided by n, is multiplied by the logarithm of n. So is the penalty function is a little bit different from the other two cases, and it can be shown that these two criteria, IC and AIC and final prediction error, are asymptotically equivalent, but it can be shown that both will tend to choose high order models. So they suggest to select a model order quite high, and so the estimates will not be consistent. On the other hand, the minimum description length yields to estimates that are consistent. So in principle, you should consider all these indications, all these suggestions in order to select the best order. And another final recommendation is that perhaps the physical insight into the process might significantly simplify the model order selection. These are examples of the behavior of the loss function. So you have the Akaike information criterion, final prediction error, and the minimum description length. But for example, in these cases, you can see here that all these cost functions seems to suggest that the model order is 2, because you have grid decreasing from the model 1. This in the independent variable is the model order, and the value remains almost constant. Also in this case, of course, it seems to suggest a model order 4, but the minimum description length seems to again suggest a model order 2. So perhaps according to these indicators, it seems that the correct model order is 2. So in order to summarize, we saw many different tests that can be performed to verify the validity of a model. The choice of the appropriate model structure, it means the model order, can be based on statistical tests on the residuals, in particular autocovariance test, cross-covariance test. And to decide the appropriate, or to have an indication of the appropriate model order test, you can use some criteria such as the Akaike information criterion, the final prediction error, or the minimum description length. Cross-validation, we will see in the practical part of our experiments, is a good approach that should be used in order to understand if the model is flexible enough. But of course, it can be used if we have a sufficient number of data. Of course, most of these tests are implemented in the system identification toolbox that will be considered in the following lecture. This is an example of the autocorrelation. For example, here it seems that the autocorrelations indicate that there are some unmodeled dynamics, or perhaps you can see here that the test is violated for positive values of tau, so it means that perhaps here there is a wrong selection of the model of the delay. Again, for an order 1, you can see here that there are some unmodeled dynamics in the autocorrelation, in the cross correlation. Also, you can see here that in the cross correlation, perhaps you see, for example, I don't know if there are some values of tau negative, so it means that there is a presence of the feedback. But when you are considering, for example, an order 2, you have that the auto and the cross correlations are between the values of the thresholds. So you can say that the prediction error is white. Or you can compare also the simulation. In this case, you can see here that the simulation is very bad for an order n is equal to 1, but it's quite good for n equal to 2, even it is not perfect, but is quite, and the cost function, you can see here that is higher here with respect to this value here. And then the same, you are considering, for example, again, the simulation for a model order on a different set of data. In particular, you are considering the validation data. And then you can see here that looking at the loss function, it seems that, again, the right order is really 2 for this case. So, and when you inspect the zero pole plot, for example, you can see here that when you are considering the order 2, you have 1 0 and 2 poles, but when you are introducing 1 pole and 1 0 more, so it means that the cancellation, according to this effect, you have 1 pole which is very close to the 0. So it means that you have no benefit to include 1 more pole in your description. So it seems that really the right order is 2. Okay, thank you for your attention.